Greetings, this is Deepak, and I'm going to be presenting about quantum computers and Turing machine. My presentation is divided into two major topics, quantum computers and then Turing machine. In the topic of quantum computers, there are several subtopics. They are difference between supercomputers and quantum computers, difference between classical bits versus qubits, quantum superposition and then quantum entanglement, and then several applications of quantum computers. Under the Turing machine, we are going to be seeing about the components of Turing machine, operations of Turing machine, and then a couple of examples which can be performed in the Turing machine, the church thesis, and then finally the halting problem. Now, what is a quantum computer? A quantum computers are machines that use properties of quantum physics to store data and perform computations. This can be extremely advantageous for certain tasks where they could vastly outperform even our best supercomputers. Now, the difference between supercomputers and then quantum computers. Supercomputers cannot be compared to the speed of and the power of the quantum computers because they can handle several computations at once. They are perfect for handling challenging issues that call for processing enormous data efficiently. Supercomputers can handle greater variety of jobs, but they can handle only one job at a time, which is a disadvantage. In this case, a quantum computer can handle several jobs at once, making it more efficient than a supercomputer. Now, a difference between bit and qubit. A bit is nothing but a representation of data in the form of either 0 or 1, whereas qubit, also called as quantum bit, is the representation of data in the form of a spin of an electron or an orientation of photon. In simple words, the physical phenomenon of a particle. Classical computers, which include smartphones and laptops, encode information in binary bits that can either be zeros or ones. In quantum computer, the basic unit of memory is a quantum bit or a qubit. Qubits are made using physical systems such as the spin of an electron or the orientation of. For instance, 8 bits are enough for a classical computer to represent any number between 0 and 255. But 8 qubits is enough for a quantum computer to represent every number between 0 and 255. Isn't that mind-blowing? A few hundred entangled qubits would be enough to represent more than numbers than there are atoms in the universe. That's interesting, right? Let's go on to the next topic, superposition versus entanglement. Quantum superposition can be explained as physical systems can be in many different arrangements all at once. There are really no definitive reality before the measurement, and the object is in an undefined state known as a superposition. This can be explained by taking two Schrodinger cats. There are four possible states. There is no relation between each state. That is, there is 25% chance that the cat is either dead or alive. Now, speaking about quantum entanglement. Quantum entanglement is the phenomenon that occurs when a group of particles are generated, interact, or share spatial proximity that the quantum state of each particle cannot be described independently of the state of others. For example, I would take the story of two electrons. Let's say that these two electrons are generated in an environment and they are entangled quantumly. These electrons are now separated 1 or 2 light years away, and we observe only one electron. This electron, let's say, has an upspin. By observing this electron, we can easily predict the spin of the other electron, which is 1 or 2 light years away, without even observing that. This we can say that the other electron has downspin since this observed electron has an upspin. This is called quantum entanglement. For example, in this instance, we can take two Schrodinger cats and it has two states. Each state is dependent on each other, and then there is 50% chance that the cat is either dead or alive. Now, let's see the applications of quantum computers. There are so many applications of quantum computers. Let's take a couple of it and then analyze them. The first example is drug design and development. Designing and developing a drug is the most challenging problem in quantum computing. Usually, drugs are being developed via the trial and error method, which is not only very expensive but also risky and challenging task to complete. It requires so much manpower, so much computing technology to be accomplished. Researchers believe quantum computing can be an effective way of understanding the drugs and its reaction on humans, which in turn can save ton of money and time for drug companies and reduce the manpower and manufacture drugs in a more efficient manner. The next example is going to be cybersecurity and cryptography. The online security space currently has been quite vulnerable to the increasing number of cyber attacks occurring across the globe on a daily basis. With our increasing dependency on digitization, we are becoming even more vulnerable to these threats. Quantum computing with the help of machine learning can help in developing various techniques to combat these cybersecurity threats. Cybersecurity is a very important thing to look into it, and quantum computing can help efficiently overcome this issue. Now, let's talk about Turing machine. A Turing machine is a theoretical device that can manipulate symbols on tape. According to a set of rules, it is used to accept recursive enumerable languages. It was invented by Alan Turing in the year 1936 as a model for computation and has been used as a fundamental concept in computer science ever since. In the context of automata theory and theory of computation, Turing machines are used to study the properties of algorithms and to determine what problems can and cannot be solved by computers. A Turing machine, in simpler words, is just a tape which has several, which holds several alphabets such as zeros, ones, any alphabet between A to Z in the tape, and it can be modified, deleted, or created. Now, let's see about the components of a Turing machine. A Turing machine essentially contains a tape, a head, and a state register. The tape is the main storage component of the Turing machine. It is divided into cells, each of which can hold symbols from the machine's alphabet. The alphabet being 0 or 1, A to B, or any special characters. The head at any point is the machine's operation, is positioned over one of these cells and a state selected from a finite set of states. At each step of its operation, the head reads the symbol in its cell. State register. The state register stores the current state of the Turing machine. The machine transitions between states based on current state and the symbol read by the head. Moving on, let's talk about the major operations performed by a Turing machine. There are three major operations that can be performed in a Turing machine. One, we can read. Two, we can write. And then the third, we can move. A Turing machine reads the symbol at the current position of the tape. A Turing machine writes a new symbol at the current position of the tape, essentially modifying the bit or the alphabet to perform an action. And then finally, a Turing machine moves the tape head one position to the left or the right. This left or right instruction is read by the Turing machine from the state register, which is the instruction provided by the state register, and then the head of the Turing machine moves left or right. Now, let's take a few examples of Turing machine. The examples of actions and computations that can be performed on a Turing machine. First example, addition. A Turing machine can be used to add two numbers. The input tape contains the two numbers separated by a blank symbol. Blank symbol usually represented by the capital letter B. The machine reads the numbers and writes the result on the output tape. So the second example is a palindrome. A Turing machine can be used to determine if a string is a palindrome. The input tape contains the string. The machine reads the string and writes yes on the output if the tape is a palindrome, or no if the tape is not a palindrome. Finally, let's see about the search thesis. In 1936, a method named lambda calculus was created by Alonzo Church, in which the search numerals are well defined, that is, the encoding of natural numbers. Church proposed a hypothesis called the search thesis that can be stated as the assumption that the intuitive notion of computable functions can be identified with partial recursive function, which is quite complicated. Simplifying that, we can say that every computation that can be carried out in the real world can be effectively performed by a Turing machine. Yes, that is the search thesis. Now, let's see about the halting problem. The halting problem is one of the major problems that was come across when the Turing machine was initially theorized. Given a program or algorithm will ever halt or not. This is the halting problem. Halting means that the program on a certain input will accept it and halt, or reject it and halt, and it would never go into an infinite loop. Basically, halting means terminating. So can we have an algorithm that will tell that the given program will halt or not? In terms of Turing machine, will it terminate when run on some machine with some particular given input string? The answer is we cannot design a generalized algorithm which can appropriately say that a given program will halt or not. Then how do we know if the program will halt or not? The only way is to run the program and check whether it halts or not. Now we are at the end of the presentation. These are the references which I used to make the presentation and gain some knowledge. And then finally, thank you so much for listening to my presentation. Have a nice day. Thank you.